Hello, everyone. So today we are going to be ending our conversation on reactors by looking at the wonderfulness that is a flow reactor. So we already started this conversation by looking at constant stirred tank reactors, or CSTRs, uh, which essentially function uh, as a batch reactor where I have a slow input and output of reactants. Now, the biggest limitation of a CSTR is the fact that the rate is going to be dictated by the concentration of the system. Now, the real unfortunate part here is the concentration of reactant in the system is going to be directly related to conversion percentage. So the more efficient a reactor, the bigger and slower the reaction will take place. So essentially, the way to improve a CSTR is to split it up into series so that each reactor is going to have a slightly higher concentration than our product outflow. Now, if you put a whole bunch of these in series almost infinitely, what you end up is a straight pipe, which is called a plug flow reactor. So the idea with a plug flow or continuously flowing reactor is going to be that the reaction rate is going to slowly decrease as I proceed down the reaction chamber, which means that the input would have the same efficiency as for a CSTR, but I get improved efficiencies for everywhere upstream. So as a net, this tends to give me a much more efficient reactor. And we can end up providing the exact rate of reaction of the reactor, again, as a function of the change in concentration versus the change in residence time. Now, where we end up having a big advantage here is that it turns out that the residence time will be directly related to the position in the reactor as a function of flow rate. So as long as I know the flow rate, I can substitute this residence time for the position in the reactor, which, let's be honest, is a really nice feature. But what ends up happening is that this means that my rate of reaction is going to change as a function of position. So in order to really predict the rate of the reactor overall, what I'm going to need to generate is an exact function of how the rate changes with position, which means usually trying to generate some sort of graphical relationship. So this is often going to be needed to be determined from experimental parameters because it will include such things as the rate constant of the reaction, as well as any first, second, third, or even half order behavior that may be present. But using these sort of relationships, it's going to actually be possible to determine the volume of the PFR of the plug flow reactor required to reach a certain percentage of the conversion. Now, it is worth noting that you will need some information as to the diameter of the system in order to be able to convert position into volume. But we can actually generate an equation for the volume of the reactor as a function of the flow rate of the initial input of A into the system. So again, FA is going to be the flow rate of a reactant A into the system. And then we're going to have is essentially an integration of 1 over the rate of the reaction as a function of position. So again, it is worth noting, while this does look simple at first glance, there is going to be a position dependence for our rate. So watch out for that. So if you have a function of R, what you're going to end up finding is that the rate's going to slow down as the percentage of conversion increases. So if you want a higher percent conversion, you're going to need a much larger volume. And in fact, as you can kind of see here at the top, we're actually really unfortunate, as it means that the volume is generally going to increase exponentially as a function of conversion percentage. So this is one of the things to watch out for, is that if you're wanting to go from, say, a 90 to 91% conversion rate, you're going to have to pay a lot more than, say, going from a 20 to 21% conversion. So again, watch out for that exponential scaling. Now, one of the things that is worth noting is that since a plug flow reactor is essentially almost the ideal form of a constant stirred tank reactor series, they have excellent conversion rates for their volume. It's really hard to beat them. As you can kind of see from this diagram of a real plug flow reactor, they can actually be fairly simple to build and easy to maintain for their conversion rates. However, it is worth, as you can often build them with simple off-the-shelf parts. However, you do often need to make use of fairly good pumps, and they have some problems with heterogeneity, because it turns out they're going to have absolutely no horizontal mixing, and the vertical mixing tends to also be very limited. However, it's not uncommon to put in baffles into your PFER that help fight this sort of ill-mixed behavior. But one of the biggest problems is because of this ill mixing, you can end up with some rather unfortunate high concentrations of products or reactants, which can occasionally result in the formation of deposits and degradation of the reactor itself. But again, one of the similar problems is that if we have unfortunate pockets of high concentration, this also can mean we can generate high pockets of temperature. So some of these large temperature gradients can be rather unfortunate for the system, especially if you're building it with off-the-shelf plastics, where we can have some degradation. So one of, again, the easiest ways to address these issues is by trying to build in mixing reservoirs somewhere in the middle, as well as introduction of things like baffles. However, there is one big problem here in that we're assuming perfect mixing of our materials, which means that everything has to be in the fluid state. This can be real problematic if I need a catalyst. So what's going to be the best way to end up adding a catalyst to the system? So if you were having a organometallic catalyst, it might actually be possible to suspend the catalyst in the flowing solution. But if I need a solid catalyst, well, that tends to be a different solution. And the answer is actually as simple as you might think. It's literally to pack in solid catalyst into the reactor, thus yielding the name packed bed reactors. Now, one of the real unfortunate parts is that unlike the previous reactor where we had horizontal flow, in that case, you find your catalyst will tend to spread out a little bit too much. So what we can tend to do is load our plug flow reactor with the catalyst we need. And what we can do is break up our catalyst into small particles. So this has a big advantage of drastically increasing our surface area, which will increase our rates. And then simply putting them on top of a filter to prevent any loss of catalyst, which is a major cost consideration when dealing with catalytic systems, especially as they often are composed of rare earth metals, which I definitely don't want to lose a nice gram of iridium. So this ends up helping face a lot of issues. However, if construction constraints mean that you need to be flowing your system in a horizontal basis, it is also possible to suspend your catalyst in between two filters, which should hopefully keep all of the catalyst in place, but does occasionally result in some poor mixing issues. But it is worth noting that we're going to have very similar rate behaviors as to our plug flow reactors because we're still seeing a concentration difference. But there's going to be one major notable exception is where the reaction's occurring. Because I may have a plug flow reactor, but I'm going to not see any major reactions until I hit the catalyst. And then once I leave the catalytic region, the reaction should be more or less stopped. So what ends up happening is that we now have less of a dependence on the position and a little bit on the volume of the system and a little bit more dependence upon the weight of catalyst. So what we can end up doing is regenerating our equation for volume, but now in terms of weight of catalyst, so you can figure out how much catalyst we need to add, with again a dependence on the initial flow rate, the rate of reaction, but it is worth noting that this rate of reaction now has is now normalized with regard to catalyst weight instead of volume. And again, still will show a position dependence, where again, position is related to time through this flow rate. So it's worth noting that these packed bed reactors kind of bring in the best parts of a plug flow reactor with a catalytic system. So packed bed reactors tend to be very popular. So they're used for especially the use of a lot of light gas work. So one great example is scrubbing waste gas such as amine, sulfur dioxide, carbon dioxide, pretty much all of your SOxes and NOxes. And as well as a number of reactions that are catalyzed by cell cultures. So what you see here on the right is a gas scrubber, but indeed it's actually possible to essentially build in a biocatalyst by running it through more of a gel system. Now, we can start to imagine a lot of the major advantages of a packed bed reactor. So let's be honest, a packed bed reactor looks a whole lot easier to build than a CSTR. One of the other major advantages is that it's going to also tend to be a lot more effective at high temperatures and pressures, because the whole system is essentially built for flow. So it's going to be much more friendly to gas phase behaviors, and it also brings in high surface area contents on any catalyst being used. So if you're having to make use of a solid catalyst, this is one of the best reactors you can make use of. But it does actually come in with some major disadvantages. One of the biggest things that can happen is you can end up having a certain amount of heterogeneity form, especially the longer you run the reaction. This often ends up forming as channels through your bed, where once you start to form a channel, your reactant is going to preferentially follow a certain path, which means it's not interacting with the catalyst. The other problem is it can also be very difficult to replace the catalyst, as I have to shut down the whole system and then usually unload the old catalyst and reload the new. And this is often something you try and avoid as much as possible in an industrial system, because shutdowns can take a large amount of time. Now, one of the other issues is you can have some poor heat transfer properties and poor mixing. However, a well-designed packed bed reactor should hopefully be able to avoid poor heat transfer, but it's really hard to avoid poor mixing. So the answer to a packed bed reactor, to the failings of a packed bed reactor, is to essentially take the idea of a packed bed reactor and start increasing the pressure of your reactants, so you actually start using that higher flow to mix your reaction. And now with a mixed reaction system, you're going to see a lot better mixing of both our catalyst and our reactants. The heat transfer becomes much less of an issue, as it should ideally be perfectly mixed. And this is going to lead to a lot better heat transfer properties, so we can more easily transfer the heat out of the system instead of forming hot spots somewhere in the middle. So again, we perform this by essentially pumping our fluid at high pressures down from below. So at first you'd see some bubbling, which isn't going to be good. And then say we'll see some formations of pockets, which will become bigger and bigger till we get to more of a turbulent regime. Now, the ideal point is to essentially get this fast fluidization mixture where I now have a nice even mixture of my catalyst and my reactant, which is going to give me uh, high surface area and thus high rates. So really, we're going to try and aim for this fast fluidization. If we pump it too high, what we end up with is what's called pneumatic transport as you start pushing all of your catalyst towards the edges and towards the top. And this is going to reduce the amount of interaction with your reactant and the catalyst. So again, trying to hit this happy medium is one of the harder parts of a fluidized bed reactor, but it's worth it to resolve the poor mixing issues of a packed bed reactor. However, this does yield some design constraints. Most notably, it's going to require a lot higher pressures and velocities, which means a lot more pumps. And in order to maintain high enough residence times for effective mixing and reaction, it tends to mean that reactors have to actually be a lot larger than equivalent packed bed reactor, where I've kind of concentrated everything together. Now, one of the other things is because a lot of that energy is spent in suspending the catalyst, we often need to overpressurize the bottom of the system and see a large pressure drop towards the top when we finally essentially stop floating our catalyst in the system. But one of the biggest problems with the fluidized bed reactor is that we're essentially launching high-speed catalysts at the walls of the reactor, and this can cause a lot of breakdown of our catalyst, which is rather unfortunate if it's expensive, and similarly erode the walls of the reactor. So this means that our fluidized bed reactors tend to be almost the most expensive to build and maintain, but it turns out that they're usually worth it for that high rate of conversion and their ability to deal with highly exothermic reactions. Because if I tried to run this same process in, say, a packed bed reactor, I'd end up with a hot spot that may either end up killing my catalyst or overcooking my materials. So there's also often a large number of common applications. One of my favorites is catalytic cracking. So this is a topic we'll come to in a couple more lectures, where I take a long chain hydrocarbon and I split it into smaller hydrocarbons, which may see greater utility. I'm looking at U-ethylene, which is a precursor to many plastics and and organic molecules. Similarly, you also have the reverse, which is coking reactions, which is essentially the combining of heavy carbon molecules to form heavier carbon molecules and hydrogen. And I can then use this hydrogen to drive other chemical reactions. And again, things like the removal of chlorinated solvents. So again, you're going to notice that these tend to work at very high temperatures, and it turns out that all of these reactions are quite exothermic. So we now have a number of different types of reactors that can be used. And let's kind of take a look at what reactors are used for what. So two of the things we have is a pair of dehydrogenation reactions. So I'm looking at reaction 1 and 4. However, they do differ in one major respect. Reaction 1 can be catalyzed by temperature alone. And if I don't need a solid catalyst and I'm dealing with light molecules, this tends to be best suited towards a plug flow reactor. However, when I'm trying to dehydrogenate heavier molecules, I often need to make use of a catalyst, so a packed bed reactor can be a little bit better. You could imagine using, this is from an older resource, so you may end up using a fluidized bed reactor depending on the nature of your catalyst. We also have things like the reaction of ethanol and acetic acid to form acetates and water. And you are going to notice that this has a much lower temperature regime. So I'm looking at more liquid systems, which usually leads us to a lot of CSTRs. Now, note that with a longer CSTR, with a CSTR and its longer residence times, we tend to have, again, a much longer residence time. And you can walk through and see similar trends amongst some of these other reactions. If I have small molecules with high heat and no need for catalyst, a plug flow reactor is often the best. As soon as I need to include a catalyst, we go towards a packed bed reactor. The more often I need to make use of liquids, such as with the addition of ethanol or nitric acid, then we start moving towards CSTRs, and you can see corresponding lower temperature regimes and longer residence times. And again, lower pressures as well. So hopefully this gives you an idea of what kind of reactors we'll typically make use of in an industrial setting. Next week, we're going to be talking about some other considerations, such as safety, health, and cost of a system. Till then, take care.